Alright, hi everyone, welcome to the second video on chapter 10, Oxidation and Reduction. Alright, so you have already completed the first video as well as the self-practice questions within the notes from page 1 to 4. If you have not already done so, please do check in with your teachers so that they can go through the relevant parts. So just a quick recap on what was covered in the previous video, right? So I think the main thing in the previous video was learning about the various methods to determine whether a type of reaction is what we call an oxidation reaction or what we call a reduction reaction. Right, at the end of the video, I mentioned that the shortcut to remember how to determine whether the reaction is oxidation or reduction is that we can use this acronym, right, called OXGOLE, whereby GO stands for gaining in oxygen, LEH stands for losing of electron or losing of hydrogen, and to know whether there's an increase in oxidation state, that will allow us to tell whether oxidation actually took place. Right? So it can be either of these four methods to use, and often it depends on the type of question and what they're asking for. And when it comes to reduction, it's actually just the opposite. Right? So if you're looking at gain of oxygen for oxidation, then reduction will be the loss of oxygen, so on and so forth. So that was covered in the previous video. Right? In the previous video, we also mentioned that for oxidation state, there's actually a couple of rules, right, that's very, very important to take note of. Right? For instance, the oxidation state of a free element is actually 0. Likewise, if you're looking at an ion, it's actually the charge of the ion. And we also look at some of the compounds, right? Whereby in most compounds, the oxidation state of oxygen is actually a -2. The OS of hydrogen is actually a +1. And then we see that if a compound has no net charge, then all the oxidation state should add up to become 0. So these are just various rules to help us identify the oxidation state in a faster manner. So in this video, what we're going to do is that we're going to use everything that we have learned in the previous video to finally apply it to determine whether a reaction is what we call a redox reaction or not. If you recall, a redox reaction refers to a reaction whereby there is both oxidation and reduction. And to determine whether there's a redox reaction, we can actually use either of these four methods that we have seen earlier. So let's take a look at section 4 now. So for a redox reaction, as what I've mentioned and also covered in the first page, is a type of chemical reaction where there is both oxidation and reduction occurring simultaneously. Right? That means it's happening at the same time within the same equation. So what would that mean? If you look at this tiny box over here, you can see that for magnesium, based on what we understand, this is actually a type of oxidation. Reason being, it actually gains oxygen, right? So OXGOLE, we can apply it in that manner. Whereas the copper 2 oxide, which is over here, from this to the right hand side, the product, we realize that it's a form of reduction, because if you use OXGOLE, this is a loss of oxygen. So when there is both the oxidation and the reduction happening in the same equation, we'll say that this is actually a type of redox reaction. Likewise for the second one, you see in the box. So H2S went through oxidation because we know that this is a loss of hydrogen. Chlorine actually went through reduction because we know that this is a gain of hydrogen. So together, we know that since both happen, then therefore this is actually a redox reaction. Right, so this is actually what we'll be doing for the bulk of this entire page, but we are actually going to just focus on the use of oxidation state to determine whether there is actually a redox reaction happening or not. So what is actually expected of a student whenever you are attempting a question like this? Right, so first and foremost, we need to find out the oxidation state of the elements that you see inside here. So I'll be working through some examples with you, then I'll leave some for you to try on your own. But I just want to highlight 3 important things to take note of when you're writing your answer. Number 1, if as you do your calculation, you realize that this whole reaction is a type of redox reaction, you must take note of how to phrase your explanation. So if it's a redox reaction, there must be 3 parts to your answer. Number 1, what is the oxidation that took place? What is the chemical? What actually happened? Number 2, what is the reduction that took place? What is the chemical? What actually happened? And number 3, to conclude that, therefore, it's a type of redox reaction. Right, so whenever you are phrasing your answer for a particular question whereby you know that it's a type of redox reaction, you actually have to phrase your answer by talking about each of these points that we see over here. So let's get started and let's try to apply what we have learned in the previous video. So over here, the first example I have over here is respiration. Right, so respiration is a process whereby this chemical, which is called glucose, actually reacts with oxygen to form CO2 as well as H2O. So let's get started by finding out our oxidation state. You know that in the previous pages we mentioned that there's some rules, right? So in a compound like this, we know that oxygen in a compound is always a -2, right? So within this glucose itself, there's 6 of the oxygen. So we know that this is gonna be 6 of them inside, but each of the oxygen, just take note, each of them is still gonna be a -2. So this will affect how we phrase our answer later on. The hydrogen, we know that in a compound, it's always gonna be, most of the time, it's gonna be a +1. And within it, we know that there's gonna be 12 of them based on the formula. Right, so with that, we know that this is gonna be 12 of them, each of them is a +1. So when you look at this entire setup, you know that if there's 12 of the +1 and there's 6 of the -2, actually this will add up to 0 already, right? And this compound having no net charge over here, it means that total everything must add up to 0, and this would in turn allow us to infer that this carbon that's over here actually has an oxidation state of 0, because that is only the way for the entire sum to be equivalent to 0. And we know that there's 6 of them, not that it matters, but the 6 of them will all give you 0. Right? So this is actually something that we learned from the previous video. Next, let's take a look at this oxygen here. This oxygen is a free element by itself, therefore the oxidation state will be 0 as well. Right? So we don't really need to care too much about the number of it because this is just an element by itself. Moving on, similarly, each of the oxygen in a compound is always, most of the time, it's going to be a -2. There's 2 of this, which means that together, it actually gives you a number of -4. And this carbon here needs to balance up the number, and that's how we derive it as +4. Right, so these are the oxidation state over here. Moving on to the water. Oxygen in a compound is a -2. Hydrogen in a compound is a +1. We know that there are 2 of them inside. And we know that the sum of this entire thing is also a 0. So you realize one very important thing over here is that when you look at oxidation state, right, we are always focusing on the individual atom. Right, so we don't go and add up the entire sum, but we still need to know the sum because it helps us to know what is the total. Right? We also don't care about the coefficient. You realize that I don't multiply by 6 based on what I see at the front, because we are just interested in the chemical itself. Now let's take a look and see if there was really a reduction or oxidation. Very obvious, you will be able to recognize that the carbon actually went from 0 all the way over here to the right hand side, whereby there's an increase from 0 to +4. So this increase is what we term as an oxidation. Remember your ox-Golay or OS increase. And then we can also see that this oxygen over here actually went from a 0 oxygen state all the way to the right hand side here, whereby it became a -2. And that's what we call reduction, because reduction is the decrease in oxidation state. Therefore, you realize that since there's both oxidation and there's reduction, this must be a type of redox reaction. So how do we phrase it out? First, let's talk about what is being oxidized. So the explanation will go something like this. C6H12O6 is oxidized, and then we elaborate a bit more about why using the idea of oxidation state, because that's what the question wants us to talk about. It's oxidized as the oxidation state. Then we focus on the element that we're looking at, which is carbon. The oxidation state of carbon, we talk about the change, which is in this case increases. And we talk about before and after. So from 0 in which chemical? In the glucose, to +4 in which chemical, which is the CO2. So this is to explain about the oxidation happening. Then in terms of reduction, the O2 is reduced. Why so? As the oxidation state of the element, which is oxygen, and this time around it actually decreases from 0 inside the O2 to a -2 in the H2O or the CO2 actually, if you look at the whole comparison. And then we end off with, since both reduction and oxidation took place, this is a redox reaction. Right, so once you get the hang of it, you realize that it's more about systematically trying to explain to someone about what exactly are you observing. So this explanation will be clearer because number one, it helps us to understand what is being oxidized, why exactly, so which oxidation state are we looking at, what D went from, and what D became. Likewise, systematically, you can see that what is being reduced, why is it being reduced, what are we looking at, and then what D went from, and then what D became. And the conclusion is just to reiterate the point about redox reaction. Right, so this is actually how we go about phrasing our explanation when it comes to determining whether a reaction is a type of redox reaction. Right, so I'd like you to try out question B yourself. Right, so take some time and work through the oxidation state. I'll actually move on to question C. Right, so does it mean that every reaction must be a type of redox reaction? Because so far in this whole set of notes, right, we've been talking about redox, redox, redox. That may not necessarily be the case, right? So we actually have to determine the oxidation state and see for ourselves, right? So the example that I would like to present to you now is part C, and we'll take a look at how do we break down the whole question. Same thing, in a compound, oxidation state of a H is usually a +1. Since this entire chemical here has no charge, I would expect the Cl to be a -1. Therefore, +1 -1 add up to 0. KOH, potassium hydroxide. In a compound, O is usually a -2, H is usually a +1. Together, I know that there's no charge, so the K must be able to help me balance up all the oxidation state, and it should be a +1 as well. So +1 -2 +1 is 0. We move on to the right hand side. The water. Oxygen, -2, like what I mentioned, and the H is a +1, and there's 2 of them, so just nice, they balance up to give you a 0. Potassium chloride. Now, potassium chloride is a bit more special. You actually have to know that it's K plus and Cl minus in terms of the ions, right? Because it's an ionic compound. And then this will be your +1, and then this is your -1 or Cl minus. So now you look at this entire comparison again, and we see if we can identify if there's any changes. Let's focus on H first. +1 on the left hand side. On the right hand side, it stays as a +1. So nothing happens to H. Chlorine, -1 on the left hand side, compared to the right hand side, it's still going to be a -1. Nothing happens to chlorine. K, went from a +1, still remain as a +1 on the right hand side, nothing happens to K. Oxygen, -2, still stay as a -2, nothing happens. Likewise for the last hydrogen, +1, and stay as a +1, nothing happens as well. So from this you can see that actually none of the chemicals were being oxidized or reduced, and therefore this is actually not a type of redox reaction. Yeah, so then in terms of explanation wise, right, we will no longer be talking about what is being oxidized, what is being reduced, blah blah blah, because nothing is happening. But we still have to explain by saying that the oxidation states, to explain that there's no change, right, the oxidation states of all elements remain unchanged in the reaction. And how do we conclude that this is not a redox? We'll just say that since both reduction and oxidation did not take place, therefore this is not a redox reaction. Right, so I hope you get the hang of it and you see how the questions actually are being derived, right? So use that to help you guide yourself in terms of answering the question. Similarly for part D, I would like you to try this out yourself as well. Just a little hint to take note of is that silver exists as an ion of Ag+, nitrate is a polyatomic ion of NO3-, but you still have to work out what is the respective oxidation state in order to work out for part D and determine whether it's a type of redox reaction or not. Alright, so once you're done trying out the questions, you can refer to the next part of the video, and then when you go back to class, you can just go through the questions with your teacher. So the next part of the notes, we're actually going to talk about this idea called oxidizing agent and what we call reducing agent. Now, these terms are supposed to be taken literally as what it means, right? So for instance, if you hear someone say an insurance agent, right, what do you think is the purpose of that person? It must be to sell you insurance, right? If you heard of this term called marketing agent, what is the purpose of that term? It must be to do marketing for the business, right? So when you talk about an oxidizing agent, right, so an oxidizing agent basically just refers to a chemical that causes another substance to be oxidized. But what's interesting is that in doing so, itself is actually being reduced. So it causes oxidation, but itself is being reduced. And then a reducing agent. A reducing agent, in terms of what it does, it causes another substance to be reduced. But in doing so, it actually causes itself to be oxidized. Right? So these are actually two terms that you'll be seeing in this section of the notes. So what this means, basically we have went through what exactly oxidation is, what exactly reduction is. But now we're just putting a term to describe the chemical that actually causes that. Let's look at this tiny box on the right hand side for as an example. So based on what we have learned so far, right, we know that for the copper 2 oxide, CuO, to the copper, this is actually a form of reduction because there's a loss of oxygen. Right, your ox-Golay or OS increase. Right, so this being a reduction would mean that who caused this guy to be reduced? It must be the other reactant that you see over here. Therefore, we call the magnesium a reducing agent. So that's actually how this term is being derived. Similarly, if you look at the same reaction, and now you look at it from the perspective of the magnesium, it actually went from Mg to MgO, and that's a form of oxidation because there's a gain of oxygen. So likewise, who causes the magnesium to be oxidized? It must be the other chemical, and therefore we say that CuO is the oxidizing agent. Right? So basically, it just requires you to look at it from the angle of the other chemical to see whether is it acting as an oxidizing agent or reducing agent. So let's try this out for this example at the bottom over here. Right, so likewise, I will do one sample with you, and after you can try out the rest by yourself. So this time around, in order to determine whether is it a reducing agent or an oxidizing agent, you must first know whether there's an oxidation or reduction that's happening. Right, so this time around, I'm just going to use the oxidation state because this is a pure element, right? So this is going to be oxidation state of 0, copper ion 2+, that means the oxidation state is going to be +2, zinc over here 2+, that means the OS is +2, and then for copper over here, the OS is going to be 0. Right, so what do you see over here? You see that this zinc actually went from a 0 to a +2, therefore we say that zinc is being oxidized. We also see that the copper went from a +2 to a 0, and we say that therefore it's being reduced. So now let's look at it just from the perspective of the copper. So copper was being reduced. Right, so copper was being reduced. It went from +2 to 0 in terms of the OS, the oxidation state. So who causes copper to be reduced? It must be the zinc. Right, therefore we say that zinc is actually what we call the reducing agent. Now look at it from the perspective of the zinc. It went from oxidation state of 0 to an oxidation state of +2. There is an oxidation. So who causes the zinc to be oxidized? It must be the other fella, which is the Cu2+, which is the oxidizing agent. Alright, so try the remaining two questions by yourself, and then we'll go through this with your teacher back in class. And this next section, we'll actually be looking at how can we test for the different types of oxidizing agent or reducing agent. But before we get started, can I request for you to make a slight change to the notes because of the typo? Right, so for part A over here, it should be actually testing for oxidizing agent. So what I mean is that when we are testing for an oxidizing agent, we can actually use chemical A or chemical B, and based on the observation, it will help us to know whether the chemical that is present is actually a type of oxidizing agent or not. So the first chemical that we will identify over here is the use of this chemical called potassium iodide, Ki. Right. So if there's an oxidizing agent, what will happen is that the potassium iodide, the iodide ions will actually go through a reaction, and then that will actually give us a certain observation, and we will actually see a brown solution. Right. So this is actually how the reaction takes place the iodide ions will get oxidized to form iodine, right? And we know that iodine is a yellowish brown chemical, and you should see the change from a color solution to either yellow, a brown, or yellowish brown solution, depending on how much of the oxidizing agent is present. That's actually one way to look at it. Right, we'll take a quick look at a video to see actually how this process takes place as. Right, as you can see from the video, that color change is really quite vivid, but sometimes if it's not obvious enough, you may not be able to catch it with your naked eye. And that's why we also can use a different chemical reagent, which is your starch iodide paper. Now, your starch iodide paper is different in the sense that by using a certain type of paper, it actually allows you to observe a color change from a white to blue. That means the paper will turn from white to blue. Right, what exactly does it look like? Let's take a look at this video. So as you can see from the video, you see that color change, right? But what exactly is the reaction behind this? Interestingly, the reaction is the same one that we have mentioned above, right? Whereby the iodide ions will actually be oxidized to iodine. But if you recall, this should be a colorless to brown color change, right? Why is it blue? Remember that the reagent we are using here now is called starch iodide paper. And those of you who take bio or from your lower sec, you should remember that iodine, if it interacts with starch, can actually form a blue-black coloration. And that's the reason why we actually see a blue-black coloration, because the iodine actually reacts with the starch to give us that color. Now, why is that important? It's important because blue is a much more vivid and obvious color than a light brown or light yellow, and it really helps us to determine the color change that we're expecting to see if there is a positive test for an oxidizing agent. Right, so on this slide, on this page, we are looking at testing for oxidizing agent. So there's two different types. Then now let's take a look at testing for reducing agent. Likewise, there's two different types as well. So likewise, before we get started, can you help me to make the edit on your notes because of the slight typo? This should be testing for reducing agent. Alright, so in the test for reducing agent, the first chemical that we'll be learning about is to use this chemical called acidified potassium manganate 7, right? It's a mouthful, but take note of the spelling, and the formula of it is actually KMnO4. Now, please take note that this chemical must be acidified, and we do that by adding dilute sulfuric acid. If not, it will not actually work. And what happens in this reaction is that the manganate 7 ions will actually be reduced to form what we call manganese 2 ions. And the process, you actually see the solution turning from purple to colorless, or what we term as decolorization. Right, so this is actually the observation that we're looking at, and once you see that, it's actually a positive test that there is a reducing agent that's present. So let's take a look at this video to see how it looks like. So you can see that whole coloration being changed from purple to colors. But I just want to highlight that it is not always an observation whereby the reaction will actually produce what we call effervescence. Right? So somehow this video that they are doing, the reaction actually generates a lot of bubbles. But usually the reaction that you will notice is usually quite mild. You don't see that kind of effervescence happening, and it's just a turn of colors from purple to colorless. The last chemical in terms of testing for reducing agent, pretty similar in terms of name, but this is actually called acidified potassium dichromate 6, and it has a formula of K2Cr2O7. Now this is a different type of chemicals over here, but the idea is the same. In the reaction, the ion will be reduced, and when the ions are being reduced, it actually causes a color change, this time around from orange to green in color. Likewise, let's take a look at this video to figure out what is exactly the observation that we're expecting. And there you have it. With the video, it will show you that actually when it comes to testing for reducing agent, there's two different types of reagents that you can use. One is to use acidified potassium manganate 7, purple to colorless, or you can use acidified potassium dichromate 6, from orange to green. At the end of the day, whichever chemicals that you choose is really based on what is available to you, as well as what gives you the best observation. Right, but that's not all in terms of the chemicals that you can be using to test for the oxidizing agent or reducing agent. There's a whole range of them that is being presented to you over here, and any one of them can be relevant depending on what is available to you at the lab. And with that, we have come to the end of part 2 of the video.